Awesome. Thank you for the intro, Karen. Wonderful to be here. Thrilled to be the first lecture of your seminar. Hopefully, started out on a high note. Started out on a fun note. As Karen said, my name is Luke. I'm from Twilio AI. Karen already gave a better job of my background than I think that I could do myself. The only thing I would like to add is a little bit of information about Twilio, because it will color a little bit about what I talk about later. So Twilio is kind of one of these very large companies you've never heard of. We're about $50 billion these days in terms of market cap, and we're basically building the programmatic layer on top of communication infrastructure. So all calls, texts, chats that kind of exist on a lot of the common internet platforms of the day, they run on Twilio. And one of the things that we do on top of that is we build a whole set of products to support customer engagement management. So basically this is figuring out, helping our customers talk to their customers functionally. I am the tech lead for what's called Twilio AI, and that is basically our bet on intelligence being very important in terms of managing communications channels. So whether that's understanding what people are saying over the phone, figuring out what people are saying in their when they talk to their Alexa or they're on Facebook Messenger. Twilio AI, basically, we want to be kind of the brain hub of this in the future. So this is partially a pitch we're hiring. It's also partially, it will color some of the examples that I bring up later on to just kind of give you some context where I'm coming from in terms of the problems we're trying to solve on top of communications channels. So the syllabus today, my goal really for the end of today is for you to be curious. What I'm talking about today is probably a 2-semester long course, if I'm being fully honest, but that's kind of the fun. That's kind of the fun in it. It's an extremely deep topic, so hopefully I can just kind of give you a taste of a variety of different aspects of what transfer learning can do for NLP and for conversational intelligence in particular, but really kind of just give you a little taste of a couple of different dimensions. So I'm going to try to really ground what the problem is today. So when people say conversational understanding, conversational intelligence, what do they mean? I want to talk a little bit about tactically what is transfer learning for NLP, discuss a couple engineering considerations at a very high level. We're not going to get into the nitty gritty. And then a very high level case study towards the end of how you can use kind of this framing of transfer learning and applied conversational understanding to solve a real problem that you might run into. So let's jump right in. I'm going to be keeping track of time since I want to make sure we hit all the notes that I want to hit. So let's talk about a couple very quick defining characteristics of language to really try to motivate why we might need transfer learning later on. So language is explicitly constructed. It is not a natural signal that exists in the world. Humans construct it to communicate ideas and intents to other humans. These are hopefully received if you speak the same language, but functionally this is deliberate. And that's a really, really big differentiator from a lot of other machine learning problems. And functionally, a language is a categorical and symbolic signaling system where I am constructing discrete symbolic representations of my thoughts and making sure that you understand my thoughts. And one of the really cool things about language, if you take my summer class, I say this, is that it's semantic encoding invariant, in that I can express the same thought in speech, in text, and in gestures if I'm using something like ASL. And that's pretty unique in terms of kind of when you think about it from a machine learning standpoint, you can kind of align different domains. You can align speech, you can align text, you can align OCR, character recognition, and functionally you know that these potentially 4 different things mean the same thing. So there's some really cool things you can do kind of based on that characteristic. Quick definitional thing. People kind of use the terms NLP and NLU fairly interchangeably. Just to make sure we're on the same page here. When I say NLP, it basically is the entire field that deals with processing, interpreting, understanding, and kind of acting on human language signals. And then NLU is a subfield within that focused on comprehension and understanding. So it sounds very similar, but it's technically a subfield. And then using the concept of NLU, how do we define conversational understanding, which is kind of the point of today. So in my mind, this is a working definition, and I don't enter this into Britannica or anything. It's basically the comprehension and understanding of human language signals grounded in common sense, the intents they are produced with, and the world context alongside which they coexist. So I think of this as 4 different pillars. The first is just the literal, like what did the person say? And what can those words ever possibly mean? The second pillar, being grounded in common sense, is very important. That's how I know when I hear a sentence, the whale jumped out of the building. I know, like, that's a fully grammatically correct sentence. I know what it means, but from a common sense standpoint, I know that's a highly unlikely sentence. The intents they are produced with, the third pillar, like I was mentioning before, language is an explicitly constructed signal. When I construct thoughts, when I put those into these words, what am I actually trying to accomplish? And then the final one is the world context alongside which they coexist. This is a really important one when you start talking about applied conversational understanding. Am I calling to complain about my bank account not showing a transaction? Am I in a car moving at very high speeds with a lot of background noise with my speech recognition running? So there's a lot of world context around the act of trying to understand language that you might want to imbue within a conversational understanding system. So this seems way too broad. So let's try to slice this up a little bit. This is very much my words here. So once again, not something you probably want to put into Britannica, but I think it's a really good mental model for how to think about conversational understanding. So I like to think of it as terms of being passive or being active. So observer versus participant. An understanding system can be passive in that it is not in the loop. It's purely observation based, where I can maybe answer questions about what happened in a conversation. I can tell you whether that conversation resulted in a sale. I can tell you whether that conversation resulted maybe the transcript of an interview, whether that person got hired, things like that. Versus an active system where that AI agent basically is participating in the conversation and it's self-constructing explicit signals with some intent. This is a much harder problem. I now need to not only understand what's going on, but I need to be able to generate natural language subject to some intent and goal that I might have. So there are a whole litany of, conversational understanding subproblems that are worthy each of like a multi-week unit. Reading comprehension, common sense reasoning, which I was talking about before, like how do you figure out what's more likely in the world? Dialogue state tracking, which we'll actually dive into a little bit today at a very high level. Intent understanding, what is someone actually trying to accomplish with the utterance that they're producing right now? Goal conditioning and orientation. If I want to sign into a chat system to reset my password, that's a very different intent from me being a black hat hacker signing into a chat to socially engineer a password versus someone who's trying to open a new account. These are totally different goals, and how I construct language can change based on that. And then of course, natural language generation. If you are an active system, you need to generate language in order to be a part of that loop, and many more. Like I said, we could go on and on here. But in applied conversational understanding, when we're actually trying to tactically solve a real problem, we rarely care about things like open-endedness. Can I respond to anything that comes my way? We usually have a very specific thing we'd like to solve or a specific answer we'd like to get at. And the unfortunate truth is academic data sets are utterly and totally useless for this by and large. These data sets do not match the way humans actually construct language for the most part. And today, we're not really going to get into natural language generation at all. We're going to be entirely passive. And just to kind of try to ground what I mean by applied conversational understanding, towards the end, I'll walk through a high-level case study on basic dialogue state tracking that I think hopefully we'll kind of see how you can take a potentially very big question and narrow it down into something that's like super tactical that you can solve in a couple of weeks. So the working definition for today for applied conversational understanding is being able to accurately and reliably determine useful characteristics, qualities, and state within an observed conversation. This is obviously a much less lofty goal than conversational understanding. We just want things to be figured out about a conversation that are useful. So now that we kind of understand what conversational understanding is, let's take a little bit of a detour here and talk about transfer learning and NLP. So what is transfer learning? I'm assuming some base level knowledge and kind of the problem framing of machine learning. But basically what transfer learning is, if I have a model or system trained on a specific task or domain, it potentially can be useful for a brand new domain. So if I have a model that's really good at identifying tables and chairs, dining tables and chairs, that might be really useful if I fine tune it a bit at looking at sofas. But functionally, what transfer learning is the ability of taking a model that's trained for a specific task and adapting it to a new task. The really powerful thing is when I can train a model on a specific task, call it task A. But task A is really easy to get data for, tons and tons and tons of data. And task B is similar enough. I can, with a little bit of fine tuning, take what I learned in A and map it to B. In this particular case, this is kind of where people like to talk about the power of transfer learning. This is kind of where it comes in. If I have the ability to just learn on an absolute ton of data, and then when I remap it, it's still useful, and I can do that remapping with a smaller amount of data. That's really, really useful for a lot of problems where it's very expensive to collect data, laborious to collect data, or it's just kind of physically impossible. You see a lot of very useful, a lot of useful data, a lot of useful applications of transfer learning in domains where you have very rare signals. So in insurance, for example, you oftentimes don't have that many instances of fraud. You might have over a year, I don't know, if you're a small provider, maybe a couple thousand instances of fraud. That might not be enough to train a very expressive model, but if you're able to use transfer learning, you can still get a model that's very good, that is very rich, but you don't need millions and millions of example data points. So let's kind of look at this in a picture. So this is the start of a pictorial that I like to use in my general deep learning for NLP class, but I'm going to augment it to look at the case when we have transfer learning. So in general, when we're doing machine learning, we want to get some raw data, and we ideally want to do some useful things. And machine learning is composed mostly, in a traditional sense, of designing really good features and then optimizing the weights of your model. Maybe it's a linear model, maybe it's some shallow neural network, some SVM, boosted decision tree, whatever you want. But this is the part that's really hard. Designing good features takes usually a PhD. You need to be a subject matter expert at least, and frankly, it just takes a lot of time. You need to understand a lot about maybe linguistic structure to design good language features. And it's just a very laborious process. This is easy, on the other hand. Training the model, usually it's a single call in a library. With deep learning, this image changes, and basically you are learning good features while optimizing the entire system. So in theory, should be significantly easier. But there's a downside here. You need lots and lots of data to make this work, usually. With transfer learning, this image changes slightly, where now most of the problem is just kind of picking, I'm going to use NLP in this case, picking a good pre-trained language model that has good features that are useful for your problem. And then a small part of that is just kind of fine-tuning it for the task that you actually want to be solving. And the beauty is that the amount of raw data you need goes way, way, way down because you have a language model that knows about language already, that understands sentence structure. You just need to remap it. You're taking that domain A, it's a lot of data, mapping it to that domain B with a little bit of data. But from domain A, we're learning a lot about language already, so you don't need to relearn all that. We're just learning kind of domain-specific things. So transfer learning, at least right now, NLP is in what's called its Imagenet moment. If you're familiar with the Imagenet challenge, it was a data set of 1 million images with 1,000 classes that kind of changed the way computer vision was done. It's maybe a little bit of an over-narration, but it really kind of broke open kind of the field of deep learning applied to computer vision. And in NLP, we have a kind of a similar thing going on right now with a lot of very large transformer models. And essentially all of these models are trained on big unlabeled data sets. So there's no labeling or human annotation required. And these transfer really well to other tasks of interest. And there are kind of two ways of doing this. Number one is what's called math language modeling, which we'll get into in a second. And number two is traditional language modeling, which we'll also get into in a couple minutes. There's kind of been a whole Sesame Street of models, I like to call, because you've got BERT, you've got Ernie, there was Ernie 2. It's a whole Roberta, Albert. There's a bajillion names of all these models that have come out of all the big companies now. And I would like to do this because it's a little bit ridiculous. Every week there's a new model coming out that beats everything else. Very hard to keep up, but kind of the key insight into what you're doing, which is taking tons of unlabeled data and training a big language model that understands language, and then fine tuning that to what you care about, that is the same across all of these. So there's really nothing kind of particular about each of these that is really important to know when talking about transfer learning at large. So let's look at math language modeling for a second. We'll use BERT as kind of the way of uncovering what math language modeling is. And there are kind of two key ingredients that go into BERT. This math language modeling thing, which I haven't described that I keep on mentioning, and something called next sentence prediction. If you do have an NLP background and you're familiar with continuous bag of words, you'll notice the picture I'm about to show, the next slide, is very similar to continuous bag of words, just mostly deep learning edition. So let's look at what math language modeling with BERT looks like. So let's say we have a sentence, we have a set of utterances broken down into two sentences. We encode kind of the beginning, the separation, and the end of these sentences, and we mask out individual words in these sentences. So this is where the masked and masked language modeling comes from. Now, it might be a really useful task to be able to predict what was masked in this sentence. If I can have a model that can predict that the first mask is seen, that model probably knows a lot about language. So if we construct kind of this big transformer model that will go through and predict out per mask what the word was that should have been there. So in the first case, it would be mask. In the second case, it would be movie. Now I mentioned that second ingredient, next sentence prediction. In next sentence prediction, functionally, we're just saying whether or not these two sentences should follow each other. And in this case, they do follow each other. And you train this over a large unlabeled corpus where you pick randomly some sentences that do and don't follow each other. And it turns out the model that can perform this task of filling in the blanks is very, very good at transferring to other problems like sentiment classification, question answering, etc. Let's look at language modeling now, so non-masked. We'll look at GPT-2 from OpenAI as an example kind of architecture of how to go through this. And essentially what you're doing with language modeling is it's a bit more probabilistic in nature than math language modeling. You essentially want to model the probability of getting any given sentence in a document. So you want to model this big joint probability. And ultimately what you end up doing is by factorizing it using Bayes' rule, you can kind of get to the point where you've got this conditional probability that is saying, hey, look at all the words that I've seen up until this point, predict out what I'm going to see next. And it turns out if you can do this really well, the features that you learn are very useful for other downstream tasks. So what does this look like? If I start from a sentence, I'm predicting out what the next word should be, then predicting out what the next word should be, and doing this over and over again. And the sentence, have you seen the expanse, appears. But essentially what I'm doing is that every single step in here, I'm predicting what the next word should be. And then based on how right or wrong I am, I'm updating all of my internal state in my model. And the model that does this can also do a lot of other things. This is very easily adaptable to other natural language generation tasks. Also very good at adapting to sentiment tasks. Basically, there's kind of a whole decathlon of problems in natural language. All of these models are at least above average at adapting to kind of any variety. So whether you're doing natural language inference, where you're comparing whether two sentences entail each other, or you're doing text classification, these models tend to be very useful. So kind of tips or maybe isms to go by. One really interesting thing you can do, I can say publicly that we actually do this at work, If you have a lot of access to unlabeled data in your domain, you can actually fine tune your BERT model or your GPT-2 model to your domain. So maybe I work in, I don't know, auto sales, and I have a bunch of chat transcripts of people trying to buy BMWs. I can train BERT to be better at filling in the missing words for chat transcripts of people buying BMWs. And now when I want to do anything on top of that, like figure out when someone wants to buy a 5 Series versus a convertible, my model is going to be much better because I've adapted it to my domain. One really interesting quirk that you'll oftentimes find is that in real systems, you don't want to fine tune your whole model. So we take this big language model and we usually have a final layer at the end that adapts it to the problem we want to solve. In a lot of systems, we'll talk a little bit about this more later, you only want to fine tune that very last layer simply because it makes your engineering life a lot easier. Instead of having a unique giant model per thing you want to solve, you have kind of a common base and then a bunch of almost like heads, if you want, that can attach to this model that perform the different tasks you care about. One of the most important things, I think, if we're doing transfer learning in the real world is like 90% of how well you do has nothing to do with the model you choose. It has to do with how much kind of mental energy you spend on collecting data. I mentioned earlier that academic data sets don't map to the real world at all. That is 1001% true, especially with transfer learning where you need very much smaller data sets. Just invest that time. The return you get on that is massive. I can't say that more times. One interesting little tidbit is you'll oftentimes find in real problems that you care about not only kind of these deep representations that are very rich with kind of multifaceted semantic meaning, but you also just care about like, did the word credit score appear in the document? One really interesting kind of tip for doing this is a paper from Google from a number of years back called on wide and deep models. I've seen a lot of companies find a lot of success combining wide and deep with transfer learning for NLP, where you have kind of a base BERT model, base Roberta model, whatever you want, that's producing some kind of very deep, rich representation. And then you have some other very sparse representation like TF-IDF, just regular binary featurization of text. And you combine both of these into a linear model. This kind of gives you a little bit of the best of both worlds. So it gives you both this kind of rich semantic understanding and kind of the very coarse, hey, was this word in the document or not, which can be very useful depending on the task you're trying to solve. And in this particular case, the BERT is not learned oftentimes. The BERT is just kind of kept as is, the one that you pick up from Google or PyTorch transformers or whatever you use. The rest is then learned. Let's touch briefly on a couple engineering considerations that come when you're working with transfer learned models. So the power here is you can fine tune really, really big models that you could never do otherwise because you don't have enough data. But that means you get all of the fun, and I really have fun in square quotes here for a reason, that comes with deploying a big model. Sure, you now from 50 examples were able to train an amazing model that does whatever you were trying to do, but that model is 8 gigabytes in memory, or that model is 24 gigabytes in memory. How do you deploy this? So we're going to take a little engineering detour here. In normal times, when I have a model that's not massive, I have a model, I stick it in some container, some virtualization of some sort. It can be bare metal if you want. And then if I have users that want to hit it or some other consumer service that wants to use that model's outputs, I just kind of stick a web server in the middle and voila, I've got a system that can now serve model requests. This is really easy to horizontally scale, assuming that the model is small enough in size. Now, if the model is very big, or you have a lot of models and they're reasonably sized, this can be very, very expensive. And with a transfer learned model, if you're fine tuning an entire BERT, this can oftentimes be prohibitive. This means you're running an entire GPU server per model that you're running. And if you're running hundreds or thousands of models, it becomes cost prohibitive. So what do? You kind of factorize the problem a little bit. So when I was saying earlier that you oftentimes don't fine tune the base of the BERT, this is a really good case for not doing that. If I can factor out that model base and create my own little service that can receive requests to figure out what the vector representation is for a piece of text, I now can have one centralized model base and then kind of a whole satellite hub of models that consume the output of a common BERT model. So I can just have one service running things through the giant model, and then all of the kind of simple linear models that are built on top can all be very cheap and spun up around that. So this is kind of one of those cases where the engineering can actually inform how you go about training your model. So if I'm working with my machine learning engineering team, I'm going to ask them to not fine tune the base so that we can all consume kind of a common set of weights at the core. And this can allow a team to scale to much higher request throughput. So like I said before, this only works if there's a shared base. And the cool thing is if you do keep the bottom frozen and you do fine tune the top from a common base BERT, you can be solving a litany of different problems. I can be solving intent classification, some common sense ranking, query re-ranking, Q&A. Each of the tops of these models, all very cheap. The bottom is the expensive part, and I just run one of those. So this can have a massive amount of savings if you're in a situation where you don't want to break the bank to run all of your models. So in the time we've left, I want to go through very high level a case study that goes from kind of the big problem statement down to tactically what you can do to solve it in a more conversational, in like an applied conversational setting. So here's the problem. Let's say we run a travel company. That should be a travel company, not untravel company. Luke's common sense re-ranking from BERT, not good. But let's say we want to make sure that when a customer wants to buy plane tickets, let's say the chat agent at the other end of the line offers them a discount. Maybe we've got a promo, we've got way over allocated seats. We need to just kind of get rid of them as fast as we can. We don't care if we take a little bit of a loss. So this is something that I can speak from personal experience at Twilio and a number of other companies. These sorts of problems come up everywhere. When I have a customer who looks like they're going to leave our platform, I want to make sure my agents give them a discount code. There's a whole variety of things that look like this. If I want to make sure that when someone calls the Stanford University Registrar's office, that the first thing that they ask for is their SUNet ID, and that's thing 0 that happens, that it also fits into this general kind of flavor of I care about the sequencing of events that happens on a call. I mentioned at the beginning this thing called dialogue state tracking. This is kind of a classic application of dialogue state tracking. Dialogue state tracking is a very big field, extremely deep. It touches on a whole lot of graph traversal problems and very interesting, very rich problems that you can go very deep into. But if you zoom out a bit, you can actually make it quite simple, and you can solve very tactical problems fairly easily, which is quite cool if you're someone who's in the business of building a product to actually solve a problem. So assumptions that we'll go into this particular case study with. I'm going to assume we're working with chat logs. We could assume we're working on recorded phone calls. As a Twilio employee, that's very near and dear to my heart, but that just adds a whole bunch of complications, and we're not giving a lesson on speech to text. We can assume we have access to annotators that can label a reasonable amount of data. And I'm also going to assume we have access to some sort of BERT model, maybe in a deployment architecture like I mentioned before, where we've got a BERT base, and then we've got a bunch of models we can run kind of the thin final layers on a bunch of other web services. So this problem statement of when someone mentions they want to buy a flight, make sure that you offer them a coupon. We can model this any number of ways. The easiest way to model this, and I think is actually very powerful and will allow you to get off the ground on a problem like this very quickly, is to model this simply as 2-sentence classification problems. You can model this in a variety of other more complicated ways where you're learning, for example, transition probabilities between different states, and you can actually model your conversation as a finite state machine, and you can learn a finite state transducer that acts on this, but you can actually get very far with 2 sentence classification models. So with 2 kind of layers of the problem, number 1 being intent, and number 2 being whether or not an offer was offered, you can kind of make meaningful progress here. So in this particular case, I'd want to break the problem down into, was a flight purchase mentioned in the sentence? That's one classification problem. The second classification problem is, was there a coupon mentioned? And if I have access to BERT Roberta, and let's say I'm able to train on unlabeled transcripts, unlabeled chat transcripts, because I've been running this company for a decade, let's say, I now have a set of very powerful language models that's tuned to my domain. I have 2 different utterance classifiers now. I can use the vectors that come out of BERT or Roberta or whichever other transformers model I want to use. And I can get utterance classifiers, in this case, 2 binary classifiers. So in the case of the first model, where I'm running this make flight purchase model, I want to collect data for each intent class. So in this case, a flight purchase wasn't mentioned versus a flight purchase was mentioned. Interesting little tidbit here. I mentioned a little bit earlier that data collection is very important. This is a classic example of where you need to be very careful in how you define no flight purchase as a class. A lot of common language elements are used between making a flight purchase versus making a train ticket purchase versus making a concert ticket purchase. Like if you just match on the words ticket and buy, you're probably going to get a lot of false positives. So this is a really important example of kind of curating the data that you collect to make sure you can cover all of the negative cases that might be confused with the positive case you care about. I can speak from personal experience. This type of situation arises all the time. And now, kind of if we build a model that can perform this binary task per utterance, per utterance in the conversation, we will basically have a probability of this sentence representing an attempt to purchase a flight. The same thing goes for whether or not a coupon was mentioned in a particular sentence. In this particular case, I can't imagine a ton of ambiguity between whether a coupon is mentioned or not. I mean, of course, there are a number of ways of saying, like, just so you know, we have a promotion this week, blah, 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 that is basically mentioning the coupon without mentioning the word coupon. And in this particular case, if we collect a data set for this problem and train on top of a good BERT representation, we can now have basically a probability of a coupon being mentioned per utterance. Now, if you combine this all together, you can look per utterance and track on the right, you can kind of see it on the right-hand side here, you kind of track the state transitions of where we are in the conversation at any point in time. So in this case, obviously a very short transcript. But the first sentence that's said is like, hey, I'd like to buy 2 tickets on United to Austin, please. So in this particular case, we would trigger our make flight purchase model. The next sentence down the line, the coupon is getting mentioned, and that's triggering the coupon mentioned. And then we can kind of go on from there. But the really important thing is we've got 2 models that right away are figuring out these 2 different transition points that we want to solve this problem. So we're taking a problem that on the surface sounds like, oh, we're gonna need to figure out a lot of characteristics about this conversation, and really kind of breaking it down into 2 very simple classification problems. And like I mentioned before, this is a general approach, kind of taking conversational understanding problems and kind of boiling them down to repeated classification problems. That's a pattern that I've found, and also just kind of through talking with other colleagues at other companies and things like that. It's a pattern that I've found to be extremely, extremely useful in solving problems that kind of have a slightly deeper level of understanding required to kind of make headway. So with that being said, a couple concluding remarks just on how, kind of where I think transfer learning is going, things that I think are useful to look at to next, and there's kind of tips and tricks from the trenches. One really important thing to note about any sort of machine learning, but transfer learning in particular, is that if you read kind of the internet, you read blogs, you look at tutorials, it looks way easier than it actually is. The unfortunate truth is a lot of folks who are building a lot of the wonderful tools that we have for transfer learning and NLP have a economic interest to make things seem absolutely painfully simple. And oftentimes they really are. Going from data set to model that works is really, really easy. Now, the hardest part of this is going from nothing to data set. So I really can't emphasize this enough. In transfer learning especially, there really is kind of this urge to just kind of jump in and train a model. You basically now don't have to worry about getting a very, very performant model any longer. So really kind of focus on the data. The other thing I will definitely say, tip and trick from the trench, or from the trenches, BERT and all of these models are way more expensive to run, even as a researcher working on maybe an offline problem where you want to analyze tweets for sentiment or something like this. They're way, way, way more expensive than you would ever imagine they are to run. So do come up with creative ways of leveraging a common base model and different maybe heads that solve different tasks to try to get over this cost barrier. I really can't emphasize that enough. You can easily rack up a couple $1,000 AWS bill without really thinking. Where is transfer learning going? I kind of hinted at it with my slide with the Sesame Street picture that kind of drops in with a lot of emphasis. The trend of, there are like, if you follow AI at all, there are the macro trends and then there are the micro trends. The macro trends are things like us moving towards transfer learning, us moving towards model-free RL, things like that. There are micro trends within that are happening now in transfer learning for NLP, especially, of getting smaller and smaller, more efficient models that are more data efficient and more compute efficient. I think this trend is going to continue for the foreseeable future. So it's really not worth your time. I kind of feel weird saying it's not worth your time to do something. It's not worth your time to over-index on a particular model that you see, or a particular model that a company comes out with. Focus more on kind of the concepts of, if you want to get into the details, looking at understanding transformers, understanding why BERT could work the way it does. Why is mass language modeling different from traditional language modeling? Why is that better for some problems and not for others? That's kind of the more useful mental model to kind of get yourself aligned on, rather than just kind of learning the details of how XLNet works the way it works. That won't be particularly future-proof. And yeah, and then I think the final statement on, especially when you think about conversational intelligence, this is something that can't be presently solved. So the most important thing you can do, and I harp on this all the time at work, is focus on problem framing. And that's basically what we did in kind of a fairly brief case study that we had. Focusing on going from the business problem in this particular case that I walked through to two very simple models. That's oftentimes the most valuable part. And the really cool thing about transfer learning, about the fact that we've got models that are open source now and are just able to just kind of run with, you can focus on that framing rather than focusing on like collecting millions of labeled examples to solve a problem. So I think that's very powerful. I think it's accelerated a lot of companies and research groups in ways that I think were pretty unimaginable 5 to 6 years ago. So I think it's very exciting. Hopefully I piqued your interest. And yeah, hopefully we've got some time now for some questions. And yeah, thank you for your attention.
Thanks so much, Luke. That was excellent. So many good points, and really appreciate the time to share that. I'll kick off with one question, and then we have, feel free everyone to add yours to the chat. This was really touching on what could have been a day or two worth, I'm sure, of material. If people are interested in learning more about the topics you've just mentioned, where should they go?
Yeah, so actually one of the companies that I was mentioning does have a vested economic interest in making this stuff look very easy. A company called Hugging Face. They have a number of wonderful tutorials on their website and also in their GitHub repository. If you look up Hugging Face transformers, they kind of show how easy it is to get going from like, you've got a data set, here's a state-of-the-art model in like 15 lines of Python code. So there's a lot of really, really awesome tutorials there. In terms of getting some of the basic concepts down, there's a researcher who's at DeepMind. His name is Sebastian Ruder. He curates a lot of really, really interesting kind of maybe bibliographies interspersed with narrative that kind of walk through all the major trends from a lot of the NLP conferences that have happened recently. And he's got a number of really good resource lists on his blog. I think it's sebruder.io. That's really, really good. And then there was a transfer learning tutorial done by, I think, him and the chief scientist at Hugging Face at ACL 2018 on transfer learning. That was really good. I'll need to find that one and send that maybe to Karen to send out to the class. Okay. That one, I don't know how to internet smith for that right now. But in general, yeah, Hugging Face tutorials are really, really good for getting a practical, like tactical, how do you go from 0 to 1 on something like this.
That's really helpful. Thank you. Let's see. So we have one question from Sriram. Can you please share your thoughts on frameworks to use when learning about these NLP techniques? Would you recommend any framework that can be used for learning or prototyping quickly versus then putting the model in production, and any engineering considerations there?
Yeah, it's a really, really good question. I'm glad you're asking me this question now and not like 3 years ago. There's been a really interesting divergence and then reconvergence of the way frameworks approach running computation for deep learning. So quick background, there are 2 different ways of doing basically building a deep learning framework. You can do define by run, or you can do define then run. It's basically the difference of a dynamic versus a static typed programming language. TensorFlow started out very static, has gone very dynamic. PyTorch started out very dynamic and has now provided a lot of support for going static. So at this point in time, TensorFlow and PyTorch are within approximation error isomorphic to each other, which is quite cool because I think it reduces a lot of the burden of choice. I personally tend to go with PyTorch for almost everything I do. I find it is a little easier to experiment, and I think a lot of the NLP libraries that make your life easier, like Hugging Face Transformers, like the NLP library that comes out of Allen AI Institute, they're written for PyTorch. So I think that kind of personally informs my choice, but at this point, the production experimentation parity, I don't think really exists to the same level that it did a couple of years back.
Okay, great. This question is from Trisha. She's thanking you for the awesome talk. And she says, do you have any tips for cases when annotated data for the specific problem setting are not available? If you have access, for instance, to Yelp reviews about a particular restaurant, but you actually want to classify how people feel about that particular cuisine, is there a value in using a somewhat similar data there?
That is a very good question that I think a lot of people would love the answer to. No, I think this is kind of one of the classic, and ultimately, and I put on my like tech lead manager hat for a second. Ultimately, annotating data, even if it's 10 to 15 examples, will help beyond belief. In general, things like if you have Yelp reviews and you're able to extract particular noun phrases about food items, or if you're able to extract particular cuisines, you can extract the sentence structure around the cuisine, you can run a pre-trained sentiment model to try to extract the sentiment. But ultimately, I almost always recommend try your best to annotate some data. If it's really, really hard to do so, one thing that has been working reasonably well for a number of folks is actually generating your own fake data. Whether manually kind of building it yourself or programmatically doing something like Snorkel, the Stanford group from Chris Ree's lab, to kind of programmatically generate your training data set. An approach like that might also be very useful in a case where you can't go out and collect it yourself.
Oh, that's great. Thank you. Here's another one from Sriram. Have you experimented with model pruning to help with making these models smaller, more efficient?
A little bit, actually. My fiance turns out is like an expert on pruning, which is kind of interesting. One interesting note about pruning is that it's So in general, the concept of pruning, for those who aren't aware, it's to basically say that in this giant neural network with all these different, I'm going to anthropomorphize this for a second, all these different synapses, 99% of these synapses don't actually matter. So I can remove them. This reduces the number of floating point numbers that need to get represented in order to run a computation. In general, this helps a lot with space. This is yet to be proven to help a lot with compute complexity, simply because they tend to require pretty specific hardware in order to leverage the sparsity that comes from pruning. So you've got a little bit of you win a lot in terms of storage space. You now need to store 1% of the floats that you had to before. But when you run computations, unless you are doing some sort of structured pruning that follows a sparsity pattern that an ASIC can exploit, you're in a bit of tough luck. You still end up running dense computations, even though you've got an inherently sparse problem. In general, I tend to find a lot of folks, especially doing things on mobile or any sort of edge deployed deep learning, quantization tends to be very useful, which is where you're turning floating point number ranges into 8-bit integer arithmetic. That tends to work kind of both for storage and also for compute, as you get about a 2.5 to 5x speed up from the U and 8 multiplications rather than float 32.
Thank you. That's really helpful. How about this last one from Abby? Among the 4 pillars of NLP, which one, according to you, seems to be the weakest link at the moment in light of the current developments happening in models and taking your experience from production level modeling?
By the 4 pillars, I'm guessing you meaning my, where was it? These 4 pillars? I'm assuming these were the 4 pillars.
I'd go with that.
I think the first pillar is pretty easy in general. Words are bounded in their meaning. You do have things like polysemy, where you have words that can mean multiple things, but condition on that, the first is not particularly hard. The last 3 are really, really hard, and frankly define what it means to be human, if we're going to get philosophical for a second. Common sense is, I think, one of the funniest ones, because you can have a statistical definition of common sense, but ultimately, we as humans, through all of our evolutionary kind of experience and all of our kind of innate knowledge that we have a very generalizable sense of common sense that we really have not been able to imbue in a model at all. Like the fact that if totally tabula rasa, if you tell a human a whale can't jump out of a building, they're probably also going to assume that a shark can't jump out of a building, and they will also probably assume that other animals that don't have legs and can climb stairs can't jump out of a building. There's just like a level of being able to symbolically reason in a very generalizable way that we're not even close to doing in neural nets. And then I think the world context part is particularly interesting, especially in light of things like GPT-3 from OpenAI. There's a really interesting thing that kind of comes up when you collect planet scale data sets. They tend to look intelligent just because they've seen so much data. You can memorize all the bigrams and trigrams of the world and look intelligent. And you end up a lot of these new models look like that. They appear intelligent, but it's purely through statistics. So I really don't think we've bridged the gap from stochastic learning and differentiable programming all the way down to structured knowledge. I think we're still pretty far there. So long story short, the last 3 we're running a bit behind. The first one tends to be good enough for 85% of things. And space sound sensitive, but the first one you can make a lot of money on. So a lot of effort has been put into that first pillar. I think as we go along, there will hopefully be something beyond deep learning that can help us solve the latter 3.
That's great. I do have one last question here. How do you suggest dealing with humor and sarcasm in a conversation?
That's extraordinarily hard. I'm going to sound like a broken record and say labeled data. No, but in all seriousness, sarcasm is one of the hardest things to do because it is not just this first pillar here. It involves common sense, and it also involves the world context as well as the intent that the content is produced with. So a sentence like, "Oh wow, that's great," can be like Luke giving his friend a really hard time with like the horrible drawing he just made, or it can be like me complimenting the baker on a wonderful cake I just purchased. And that depends entirely on the world context. So that's really the thing that ultimately makes humor really, really hard to detect, and sarcasm really, really hard to detect. It depends on so much shared context between the agents participating in the conversation and the world in which they exist. It's very hard to perform in isolation.
Mm-hmm.
If I'm not mistaken, there was a benchmark data set of like, there was some, I don't remember the name of it, but it was basically turns of conversation and annotated examples of sarcasm in the context of the conversation. That I think generally makes sense, and I'm not going to say can be solved, but you can at least make some progress there. But in general, in isolation, a statement is basically impossible to determine whether or not it's sarcasm or not.
Makes sense. Well, thank you again. I just had one follow-up here, and to let everyone know, we are recording all these sessions. They should be up soon, both on the seminar webpage, and we can also send to the students via Canvas. So you can check it out later if there's some piece of it that you've missed. Also, someone asked if it's possible to get a copy of the slides. I don't know if that's okay with you, Luke, but that was.
Should in general be fine, yeah.
Okay, great. Well, then we'll get a copy later and send to everyone here. And thanks again for coming today and tonight, late your time, and giving us all this really excellent food for thought. And definitely looking forward to hearing. Hopefully you can come back next year and tell us the latest on all these areas.
Wonderful. Thank you, Karen. Thanks all.
Okay, bye everyone. Have a great evening.